Hello and welcome to another video on orbital mechanics. I'm still working through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm up to problem 2.2. And this problem is very similar to problem 2.1. It is talking about a system of particles. It is asking about three particles of identical mass that are acted only on by the gravitational forces between each other, and each particle is located on the axes, on the vertices of the equilateral triangle with sides of length d, and it wants you to define the angular velocity of any one of the particles. So I'm going to draw a little picture of the triangle. That'll do. And here are the particles on the triangle. And here is the center of gravity. This is R, this is D. And we have a gravitational force. This is 1, 2, and 3. We have a gravitational force this way, which is F1, 2. And we have one this way, which is F1, 3. Now, the easiest way to solve this is to imagine, in my opinion, is to imagine this is 0 on the y-axis, and this is the j-axis, and this is 0. And we need to split the forces into their components. Now, by making this 0 on the y-axis here, we can effectively cancel out the I components of these forces. So we're trying to work it out for this particle, and it simplifies the whole thing. So if we say F, the force along the I-axis, equals for this particle equals minus g m over d squared. When we're talking about this one here, this is times cos 60, because this is 60 degrees, and this is the adjacent, and this is the hypotenuse. And then we have plus the other side, which is exactly the same. So those just cancel out and equal 0. And then we do for F along the j-axis, that equals more or less the same thing, except it is now sine 60 for the other component, and we have two of those. They don't cancel out. And so that is the force. And for this system to stay in equilibrium and to continue with an equal distance d, the centripetal force must equal the force that each particle is experiencing. So, and this is going, this is actually going this way. This is FC, and FC. It's all, well, it's supposed to be 90 degrees to that. Just like that. So FC equals m angular velocity squared times r. Now r here, using some simple trigonometry. So if we say this is right angle here, because that is also r, we know that is a right angle. We know this is 30. We can say that cos 30 equals d over 2 divided by r. And so rearrange that, r equals d root 3. Sorry, r equals d over root 3. So this is the FC circular centripetal force equals Fj, and then we can match all those up. We'll cancel an m. Angular velocity squared d over root 3 equals 2gm over d squared, and sine 60 is also root 3 over 2. Those 2's cancel, and then angular velocity equals the square root of root 3 times root 3 is 3 g m over d cubed. Okay, that's that. As you can see, making the triangle origin 0 here and angling it this way reduces the complexity of the problem. I'll put a MATLAB script up with as much of this as possible. And yeah, I got a bit kerfuffled over here, but that's it. If you have any questions, leave them in the comments. Thank you. Bye-bye.